International Islamic University in Malaysia, IIUM, and executive member of Malaysia Tribology Society, my tribos. Here is my topic today about frictions and lubrication in manufacturing. For this 3-day workshop on lubrications in automotive industry. Hope everyone listens to this exciting tribology field. Here's the outline for the seminar today. First, I will give you some brief overview about the IIUM, and then my tribals, and then about the topic friction and lubrication in manufacturing, where I will focus on sheet metal forming. What you see here is my workplace, IIUM, located at the heart of Malaysia, Kuala Lumpur. It is one of a public university in Malaysia, established in 1983. IIUM has more than
Sir, your mic is on mute, sir. Sir?
So your mic is on mute. We can't hear you.
Sir, Rao sir.
Sir, yes, sir.
And the
yes,
speaker
sir.
mic is muted, sir.
Yes,
Kindly
sir,
inform.
Yes, sir. Yes.
Yeah. Oh, sorry. Can you hear me? Maybe something.
Yes, sir.
Hello?
Yes, sir. We can hear you. Please start from the beginning, sir. The
Yeah.
first slide. Yeah. Yes, sir. Yes, sir.
Okay. So now you can see me, right? You
Yes,
can
sir.
hear me, right?
Yes, sir. Yes, sir.
Okay. So sorry about that. So where I missed this?
Please start from the first slide, sir. The first slide of
from which slide?
first slide, sir.
The first slide.
Yes, sir. Yes, sir. Yeah.
From the okay. Sorry about that.
Yeah.
So from the first slide, you mean this slide?
Next one.
Okay.
Next one.
Okay. The next one. Sorry.
Yeah. Okay. Okay,
so,
sir. Okay. Okay,
sorry
sir.
about that.
Okay, sir.
Okay. Now. Okay. I touched some setting. Okay. Sorry about that. Okay. Let's start. Here's the outline for this topic today. So I will give you some brief overview about my IUM, my workplace, my tribals, and our topic today about frictions and lubrication, and these are with application in the manufacturing processes. Here you see my workplace, IIUM, located at the heart of Malaysia, Kuala Lumpur, is one of public university in Malaysia established in 1983. IIUM has produced more than 70 graduates and undergraduates from more than 100 countries from around the world. Most of them were from Malaysia. So here you see the tribologists at my workplace, IUM, they are my tribos member. Prof. Emeritus IR Dr. Masyuki Hassan being the pioneer of this my tribos. Malaysian Tribology Society with more than 35 years experience in this research, tribology research with H index of 83, and he is currently one of the Malaysia global top 1% highly cited researcher. And there, here at IUM, we also have Prof. Dr. Malik with more than 25 year experience and H index 35, and he has published more than 300 publications. And the last one, myself, Hafis, and young tribologists. Actually, we have more tribologists at IIM. So those. Okay, next about Malaysian Tribology Society. My tribos established in 2007, and my tribos affiliates with the International Tribology Council (ITC) since 2016. So currently, my tribos has more than 137 registered members. Feel free to join us and be part of our Tribology Society. You can become our member with a yearly or one-time subscription fee. Here you see this is my tribos executive members, being Prof. Samia Kasolang being the president, and lead the my tribos, supported by vice presidents and other executive members. This is an official journal run by my tribos, Journal Tribology. You can access, download, read article for free related to tribology research. We appreciate if you could contribute to this journal Tribology. And down here, you see a link to our search engine about tribological practices in Malaysia, where you could use it to search and find all experts and articles. So some activities about my tribos. So currently we have a monthly my tribos webinar 2020. Feel free to join this event. Yesterday we have an event for this month developed by our tribology member from IUITM. So next month there will be one. So every month we have one event for this webinar, since now everything virtual. So this is our past activities, having ATC 2018, ISA Trip 2018, and my Tribal Symposium 2019, and Malaysia Singapore Research Symposiums 2019, and meeting with just Japanese members, representative for MITC MJTS 2020, and also we have we go for WTC World Tribology Council 2025 meeting in Lyon, France 2019. So for the upcoming My Tribos event, we welcome all of you today to join us at this conference, which will be held in Langkawi this year in July 2021. My Tribos also welcome industries or any organization to support and sponsor this event. Now I will share with you about our talk today, tribological studies in one of the most important manufacturing processes, sheet metal forming. But we go for the some history about tribology first. The tribology has been with us for quite a long time, starting from the Da Vinci in 1452, and then some other famous names, Emmentains, Euler, Coulombs, all these here. What we use today, all this come from them. Influence of friction in in our everyday life is here what you see making fire due to friction, sound generation due to the stick slip effect, and the braking effect, and also friction. This friction is used to enable forming processes. And what is the undesired friction? Reduction of efficiency level and tool wear, as you can see on the image here. This due to the unintended temperature increase between the contact surfaces, and this has caused 3 to 5% of GNP due to friction and wear. So here you see tribological system where it has consists of a tool, workpiece, and intermediate material, normally lubricants, oil, something like that, and also the surrounding medium. So all of this is the structure of tribological systems. So being the process parameter that influence the tribological system is the load distribution, progression and duration of load condition, velocity, temperature, and the movement, sliding, rolling, and sequence of movements continuously oscillating or intermittently. So due to this has caused wear, surface changes, and also the material losses, energy dissipation, friction, and wear. Okay, now you see the influential factors on friction, where these are due to the normal stress, which is coming from the tool, and this is due to the deformation of workpiece, and also influence of the roughness of the workpiece or maybe the tool, and the material combination between the tool and the workpiece, and also the sliding velocity and the lubricants that is in between the tool and the workpiece. And there are three factors that influence the frictions. One is the process-related influencing factors, amount of distribution of normal stress on the contact surface, and the sliding velocity, surface enlargement of the workpiece materials, change of temperature. And the second one is the material-related influencing factors, adhesion tendency, cold welding of metals of the same strength, and the chemical composition with and microstructure between the contact surfaces. And the last factor is the lubricants due to the viscosity, shear strength, pressure and temperature resistance, and also chemical and physical reactivity between the contact surfaces. So here you see the base material on the bottom, being they are boundary layer divided into two, one close to the base materials with approximate of 5,000 nanometer. In this boundary layer we call it inner boundary layer. Distortion field due to machining or maybe due to the forming processes. And the outer layer, we have the outside layer with approximate 1 to 10 nanometer, and on the far outer layer is the absorber layer with 0.3 to 0.5 nanometer. Here you see the Stribeck curve that being used for the friction mechanisms. So being the coefficient of friction mu as a function of the dynamic viscosity, sliding velocity, and also the pressure. Same goes for the flillum thickness, where the separating the tool and workpiece surfaces. So as you can see here on the top right, where the dry friction with friction, all these are based on the Coulomb friction law. So for the friction coefficient more than 0.3 with having the dry friction conditions, so they are having these boundary layers. So they are located on the far top left, as you can see here, due to there is no lubricant separating the surfaces. So and on the second, you see here The second here, boundary friction with friction between 0.1 to 0.3. But again, there is no contacting surface between them, unlike the dry friction where there is some contact due to this in some area. And here we see the boundary layer able to separate the tool and the workpiece surfaces, thereby the friction here is around 0.1 to 0.3, but then the film thickness now increase a little bit. So then when here is the interesting part for the forming technology, for the metal forming, most of the tribologists in this metal forming technology, they will look into this. They develop the specific friction equation, friction formula. In some of them called what do you call it? Hydrodynamic lubrications, microplasto hydrodynamic lubrications, and also microplasto elastic hydrodynamic lubrications. So they are having the lubricant that help to separate the lubricant. So some lubricant entrap between this area due to the direct contact between the tool and workpiece material. So this giving the friction coefficient between more than 0.03 up to 0.1. So, but for the hydrodynamic friction, which is having the friction less than 0.03, this is mostly happen in some application, engineering application like bearing. So they have the very thick lubricant. So therefore, as you can see here, the coefficient is very low, around, yeah. And also, but then the film thickness kept increasing. So due to this, but then it's not good to have a film thickness that is very wide, very thick. Therefore, the friction increase again at some point. So we need to be careful when we select the lubricant type. So now we will look into some study about friction and lubrication in sheet metal forming, which is one of the manufacturing process. Before that, let me introduce you, give you some brief overview about the industrial lubricant application in Kuala Lumpur. Okay, in Kuala Lumpur, KL, we call it KL with this name. And the biggest share is contributed by hydraulic fluid, about 29%, and followed by engine oil around 29%, and metalworking fluid about 19%. As you can see, the metalworking fluid consumes large amount of lubricant, which covers machinings and metal forming processes. So, as you know, large amount of chlorinated oils have been used as lubricant in metal forming industry. They are very polluting, harmful to the human health and the environment. Therefore, our studies aims at finding environmental friendly alternative to replace the harmful chlorinated oil. Besides, we also focus on the lubricant waste, which we try to minimize it, and at the same time we want to optimize the manufacturing process for a longer tool life and for a longer tool and lubricant life. So how can we evaluate the lubricant performance? That's the one important question here. So here we propose two methods. First is the offline testing of lubricant performance with conditions close to production condition. This is where we collaborate. Most of the time we develop one test setup, and then we develop this setup with collaborations in collaboration with some industry. For example, those for the stamping industry, for the forging industry. So now we are working together with PHN industry, which is one of the biggest manufacturer for producing the automotive components for our local car, Prodo and Proton. And the second method is the physical and evaluation, chemical evaluations of lubricant ability to bond to tool and workpiece faces. This is most of the laboratory testings, which is available in more in many universities and research institutes. So for the first method, which is the offline testing, we have designed and fabricated a bench test for monitoring the tribosystems. So this test bed can run multiple tests at a pre-sliding length, as written here, described here, sliding speed and with adjustable temperature. There are two SS, SS1 and SS2. With SS1 is a hydraulic press. At SS1 this with a tension capability of 50 kilonewtons, and SS2 here is the compression capability of the 100 kilonewton, and furnace and lubrication systems are installed before the workpiece enter the forming area. Here you see another version of universal sheet tribo tester. This one is developed by Hermano back in 2014 in Technical University of Denmark, where I used this machine for my PhD work. So this tribo tester has more axis with more flexibility. This tribo, as you can see here, it can this tribo tester can run multiple tests continuously from a coil at a pre-sliding speed and sliding length. The PC PLC equipment is used to control three axes, axis 1, 2, and 3, with hydraulic power of 50 kilonewton at axis 2 and axis 3 100 kilonewton. And here also the cutting station to cut the material after the testing, and the lubrication around this area, and also the automatic coil feed. As you can see here, some example of the, we call it multiple tests for sheet metal forming. So here you see the strip, this is deep drawing. So here you see the strip drawing with flat dies, bending under tensions, the drawing with tangential compressions, bending with tangential compressions. And these are the common one, strip reduction tests with the influence of the workpiece deformations. And here is the strip tension test, and also the draw bit test, which is mostly important for the automotive industries and also the other sheet metal forming industry, where they use this to control the material flow. And due to this, there is no excess of lubrication between the contact surface. So this is caused a very severe tribological conditions. So with the offline testing, we have developed the offline test procedure for use for this study. So with the stage 1 here, you see we visit the company, understand the problem issue at the company. So then we perform the finite element analysis first of the production platform to understand the problem. And there we have the preparing the lab test, where I design and develop lab tests based on the finding we obtained from the stage 1. Then we do the finite element analysis of the lab test that we set up earlier, that we designed earlier. Then we plan the lab test or what kind of the solution we want to propose, or then we go to the next step is the laboratory testings, which is where we do the screening test. If successful, proceed to the continuous test. Once complete and successful, the procedure complete and the solution is highly recommended for production, and we proceed to the last stage, which is the production test of the promising solution. Let's say if we found coating, we use one coating that can give some promising tribological condition without the use of lubricants. Thereby, we will do the test at the third stage first, and when we obtain that coating, we show some satisfactory result and very promising, then we will go to the company again and test them at the company using the actual tool. So I will share with you an industrial case on deep drawing. Here you see a 5-step. I can see 5 steps starting from 1, 2, 3. But here we start with 0, 1, 2, 3, and then some 4. And you see here that at this stage there is nothing happen here. It just the material just passed through it. Here is a 5-step progressing to producing a stainless steel component for the ground force. One of the company for the pump components. The operation includes 1, blanking, and then deep drawing, and first drawing, and second drawing, and then punching of the finished component. But here you see at the third stage, with secondary drawing of the strain hardened component is chosen as the tribological severe forming condition due to, if you look closely at the image here, but then why is it severe? Why we can see wear marks on this surface on the form components? So then we want to solve the problem. So we bring it to the all the measurement available here. We measure the we gather as much as possible information as from the industry where we visit, and then we evaluate the production platform using the finite element solution software. So here we use LS-DYNA software. Finite elements of the analysis of the production platform has been performed to determine the most influential process parameters in the secondary drawing operations, where the contact pressure here turned out to be large, approximately around 2.5 gigapascal. So here you see the second procedure where we prepare the lab test, bending under tensions. Again, the finite element simulation is used to save costs for fabrication and avoid trial and error. So here the tool is designed based on the finding found on in the previous procedure, where contact pressure need to be exactly 2.5 gigapascal. Similar condition to the production. So bending under tension, replicating the second redrawing of the component has been selected and refined with cutting off the top tool surface about 42-degree angle, and the contact pressure of the 2.5 gigapascal is 18. So this is the lab test where the tool and the workpiece has been fabricated based on the finding in the second procedure. So it's around here. Around here. Installing this bending under tension is set up into the universal tribo tester. The test can be performed continuously according to the operating parameters in production. At the final stage,
Sorry, and the final procedure for the second stage, we propose feasible solution for the testing in the productions. In this case, some material and lubricant were tested in production based on findings earlier. First, running the stainless steel with the chlorinated oil, good surface finish is achieved. And here, running the same chlorinated oil for forming high strength steel, DP800, severe wear is observed on the surface of the workpiece. Same result was obtained when forming the DP800 with a thin hydraulic oil that has no special additive severe scoring on the deep drawn surface. So, however, a positive result of using a thick hydraulic F2, we name it with F2. When forming DP800 is obtained, so no scoring mark is visible, meaning that F2 is capable to be used for forming this DP800, which is more environmental friendly in this case. So here you see, as recommended by the company, if the test survive up to 1500 stroke with 40 stroke per minute, this means that the solution is applicable to production. So then we come up with this table where the conclusion was drawn from both lab and the production test. All results shows good agreement between both tests except this one. So here you see a 5-step progressive tool for producing a stainless steel component. Again, still for we go and visit the Grundfos company where they are producing pump component. This is a stainless steel bearing plates for pump hydraulics. So here is the process look like in the productions. Operation 5. Ironing is found to be one of the tribological most critical operation leading to lubricant film breakdown and severe scoring on form surface. But why ironing is considered as the critical operations? So we want to investigate why first for this. So while the punch returns to its original position, the lubricants applied to the tool and workpiece surface is scraped off further when the punch moves upwards. So, and also due to the extra at this stage wear occurs between the punch and the workpiece surfaces due to the contact and extra reduction in thickness during the backstroke, where we do not expect this. We only expect the reduction in thickness during the forward stroke, but then we realized that when we do the fin element, we realized that there are some extra contributions of the reduction in thickness during the backstroke. So due to this, a double stage strip reduction test has been developed and has been designed and developed. Here you see the double stage strip ironing test has been designed and fabricated with a station A. Here ironing for the forward stroke and the station B retractions. So this is the station A, station B. So we come up with this where the station A has 24% sheet thickness reduction, while the station B, due to the retraction of the punch and another 4% contributions of the sheet thickness reduction has been also applied at this station B. So since station B causing the wear problem, so that's why we install this torque transducer here, because the torque transducer is more sensitive to identifying and measuring friction force in comparison to load measurement. This is another industrial case study with the production of one of the exhaust metal component for truck. Silverware occurs in the very first forming process, stamping just right after 200 stroke. This is what we have learned when we visit this AO steel company. They told us that they use a one-step stamping operation. They'll figure out that on site of calling at approximately around 200 strokes, and we also know about their die material and their fine setup and everything, the tool. And also we learned that the possible defect due to fracture, wrinkling, and wear on draw bits. So thereby our goal here is to investigate and evaluate the applicability of non-chlorinated lubricant. Currently they use Castrol BWN 205 as a lubricant, which is having this extreme pressure additive. So tool has been taken out from the factory, and then we want to look into the main problem leading to severe wear on the drawbit. So we measure this. We want to determine the what do you call it, the dimensions. So that's why we need to know. We want to focus on the critical tribological condition at this stage, at this tool and die setup. So here the tool was scanned, okay, with this Atoll triple scan MV 560 lens setup. So with 3 mm reference point. So again, finite element analysis of the production platform was used to optimize the thickness distributions along this of the stem part. And surprisingly, 20-30% reduction in thickness for automotive component is achieved by modifying the die geometry with more uniform thickness all over the stem sheet surface. So thereby spacing the and die radius in zone 3. In zone 3,
Sir, your voice is not audible, sir. Raghav?
Yes, sir. Yes, sir.
Sir, voice is not audible, right?
Yes, sir. It's not audible.
Sir, Rao, sir.
Yes, sir. Yes, sir.
Sir, voice is not audible, sir.
Yes, sir. Yes, sir.
Just
Yes.
you communicate, sir.
Yes, sir. Yes, sir.
Okay, sir. Okay.
Yes, hello, bro.
Yes, sir. Yes, sir. Now audible, sir. Please. Yes,
So which slide? I am
sir.
not sure.
The same, sir. The gas recirculation slide.
Maybe due to the limitation, right? So which
Yeah.
slide?
Maybe the one earlier one. Yes, sir. Yes, sir. This one. This one. Yes.
This one.
This one. Yes, sir.
Okay. So we already reached the limits, 40 minutes, right? That's why we go. The
Yes,
voice. Now can you hear me?
Yes, sir. Yes, sir.
Okay.
Please.
Okay, good. So this slide, right? So
Yes, sir.
so here you see so we took out the tool that we bring it to take out the tool and we measure it. Okay, we scan and measure the dimension so that we know the exact dimension of this tool. And we perform from there. When we scan the tool, we gather information, and we learn that when we perform the finite elements analysis of the predation platform, so we can optimize the thickness distributions of the stem part. So how do we do this? So but then surprisingly, we learned that 20 to 30% reduction in thickness for automotive this automotive component is achieved by modifying the die geometry, so that we can have more uniform thickness all over the stem part. So this is what we learned from this finite element. And here you see the spacing and die radius in zone 3, where the drop bit is placed are enlarged, and this is to reduce. As you can see here, the radius here 1.5. This is the original one, and here is 2.97, where we enlarge the radius, and in order to reduce the contact pressure. Besides, this allow for controlling the material flow. The material flow between the two upper and lower two of the sheet during stamping operations. And this here you see the finite element analysis and how we optimize the die surface by making the die geometry larger. Then this has reduced the contact pressure at this zone 3, and this also give less wear work on the die surface at this zone 3. So here you see when we perform the second stage, we now in the third stage where we design and develop and the draw bit test setup, and we mount it on the universal tribo tester using this setup. So to the left, you see the setup with original die geometry, which here we see the unstable force and severe wear. As you can see here, when we tested this with different lubricants, so this is what happened after the draw bit test. So here we use this is the BWN205 is the one we obtained from the factory, from where they use this oil, and then we try to replace with more environmental friendly oil, Renes oil that has no special additive, but this one with a thicker thick lubricants, and this is about even not thick one, but then still about 100 something in viscosity. And also this is one of the vegetable oil. And then to the right, you see the lab test setup with modified geometry, where we learn that there is nowhere visible on the draw bit die surface. All the test lubricants, either with the one with and without special additive, work satisfactorily. So we also use the same material, Sulaiman 2 material, but this one with surface treatment. We send out to the supplier to do this. So now let us focus on the second type of evaluating the lubricant performance for sheet metal forming. But this one, most of what we always do in our laboratory, we trying to figure out the physical and chemical reactivity of the lubricant ability to bond and to tool and workpiece surfaces. Okay, so we start with this physical evaluation of lubricants using a punching test. So as you can see here, the punching stats punching involve 3 steps. Being the last one is the critical one when the retraction of the punch, and this allows some the cut surface to have some deform and touch in contact with the punch surface. As a result, what you see here, there is the high backstroke force. So when the punch moves back upward to its homing positions, so this punch surface is scraped off further with no access to lubricants, compared to this one where during the forward stroke there is so many lubricants, but then lubricant has been scraped off. So but then during the retraction there is no access to this lubricant between the punch and the workpiece. So this can cause a very high backward force, as you can see here, due to the contact and extra thickness reductions. So for a further examination of lubricants were studied carefully. To the left, you see the lubricants. You see the lubrication system by roller. Okay, by roller, which is more effective than the one on the right image here. Using the lubricant channels by flushing the oil to the sheet surface before the punching process. So roller lubricators allow the punching to work satisfactorily with no failure compared to this one. So the chlorinated paraffin oil like TDN 81 that has a extreme pressure additive which is harmful to our human health and environment, and PN226 and SP125A function effectively with stable force, as you can see here, the bottom line there, for punching up to 500 hole. So Thanks. So what is the reason to do this? So then we bring the punch to look at the how it looks like with different oil. So here you see the same image of the punch surface when using the roller lubricants. So chlorinated oil PN to 6 shows good punch surface after testing with no pickup of workpiece material. This is due to the additive in that material, in that oil, where it has an extreme pressure additive that allow it to separate the tool and workpiece surface during the punching process. So in order to prove this, we perform this test. We try first with this 4-ball tribo tester in order to analyze the wear behavior and the load bearing capacity of these lubricants. So the test is performed at room temperature with test conditions specified in this table. Running the 4-ball test has led to unclear conclusions on the wear and load of the test lubricant. As we can see here, the positive result when testing with the chlorinated oil has shown that there are no wet load. Right, you see the wet load on the stripe bar, the red bar, except that high load on the large wear. So this gives us a clue that in order to find the answer using another test, is the additive in the chlorinated oil is very important. So here, pin on this tribometer has been used to assess the friction value of the lubricant as the temperature increase. So the test is performed using the test parameter as described in this table top left. With here the test material is the same material type and properties applied in the labs and also in the production test. It turns out that additive is activated in a certain range of temperature. Look at the point A to B, A to B, A to so this is the case for the PN226, Drosera MS5, and also paraffin oil. There again, we use finite element. So running the experiment with continuous tribo tester, we could only see the temperature increase. Temperature increase of the measured temperature point that was located in the die. So we put it under, we mount, we drill hole, and then we mount a temperature sensor to measure the temperature, okay, in the die. So which is near or close to a die workpiece sliding surface. This is but then it is still difficult to assess the localized temperature. That's why we use finite element simulation, but with the data we obtain from this point 1 as an input to the finite element. So now using this finite element simulation, one can analyze localized temperature at point 2 here, where the localized temperature distribution of the deformed sheet material in the shearing zone. So here you see the temperature reach about 130 degrees C at time 0.1 seconds. So for one stroke, okay, one particular stroke when we extract from the finite element. And this is exactly found in the tribology pin on this test, where the extreme pressure additive of the lubricants is activated at this temperature range. So here is the measurement of the temperature as function of the stroke. So then we also use another utilizing a acoustic emission sensor for monitoring purpose, effectiveness of the lubricants can be elevated as same as the one we normally do by defining the load as a function sliding length. So acoustic emission is a reliable method to that can be used to detect onset of lubricant film breakdown leading to wear problem. As you can see, we mount the bending annotations. We perform one test here. So we perform three testing with two different lubricants, and we learn that with three different setup, we'll normally with CR5 we're gonna get a stable stable force like this with the black one, and the torque also stable. But then still we believe that in this case you can see the difference when we use a torque. We can detect the onset of we call it calling, the onset of wear, where we learn that using this torque. This is the one with CR5 oil. This is the one with this is with CR5 oil. This is with the CR5 sign mixture of CR5 and Sun 60 oil, where we with a ratio of 50 to 50%. So we learn that. So using torque, we can see that the onset of the galling occurs. So this also has been found when we use this acoustic emission. But then, to my knowledge, acoustic emission is applicable for the lab test only. When we when we want to implement this in the industry last time, we learned that the industry, they have already installed this acoustic emission, but then it works in the beginning stage only. So, but when it is been used for maybe after sometimes it's not function as they want it to be. So because the noise coming from the production influence the results, and also the vibration coming from the other machines, from the floor, also influence the acoustic emission results. So meaning that is, to my knowledge, is applicable for the lab test only. So again, I think that's the end of my presentations, or I could say my sharing. Thank you so much for your attention. I hope that my sharing session today will give you some insightful into proper analysis of lubricants performance in manufacturing process. So where we here we focus on sheet metal forming process. Hope with this the participants today could reach out to our Malaysian tribologists, Malaysian tribology societies, or my tribos, university or research institutes for collaboration in this exciting tribology field. And so with that, I end my session with thank you so much to the organizer. I pass the floor back to the organizer. Thank you so much.
Thank you, Prof.
Thank you, sir. I asked all the participants if they have any doubts, they can put them in the chat section.
Okay. Okay, so there's one question I can ask about the burr. When it's mixed with the lubricant, is the viscosity factors influence the variations in drawing thickness and probability of surface deformations? So in this case, we do not know into the burr effect. While we learn that burr maybe it is we consider the burr as a contribution to the thickness. So that's why when the punch, I think maybe he referred to this which one, I think. I think maybe here. So you can see the slide, right?
No,
Okay,
sir.
so yeah.
Your slide is not visible.
Oh, not there. Okay, wait. Let me share with. Okay, here you see, right, the slide. So I understand about the burr effect here. So the burr on the down here, the bottom of piece, where when the material has been cut. But then we realized that when the punch move upwards to its homing positions, so the punch is scraped off further. So this is because of there is no access to lubricant. So we don't believe in this the per influence into the viscosity, and that's why we go for we investigate the additive in the oil. How is this additive influence? Because when the additives stick to the punch surface, and then maybe the additive do not peel off, they will stay on the punch surface, and this allow the punch to allow this additive in that oil to separate the tool and workpiece surfaces during the punching or during the retractions process. So, but then we still believe that this is due to the extra thickness reduction here. So that was why we do we do this, and then we perform this lah. We investigate further to know about the additive effect on this. So about the viscosity is one thing, but then still we believe it is due to the additive, not the viscosity of the oil. But then the additive it also influence the viscosity, yes, of course. But then nowadays we still believe that additive lah is the one that caused this. So am I answer your questions? So okay, so is this answer to this first question about this burr mixed with the lubricant?
Yes, Prof. Yes. I think there is another question also.
Okay.
Yeah.
Okay. So the next question is about during the tribology process, the temperature will rises, then the pin on this wave is more affected. This is more affected. That's why it suffers so much. So I think this is more common, or I think it's common, right? Yes, it's true. The temperature rises causing this effect, because as let me show you, let me share you with this slide here. This is where we, as you can see here, the temperature effect, where coefficient as a function of temperature. When we increase the temperature, this is what we figure out. The additive in the oil is activated at some certain range. That's why the frictions reduce, as you can see, by a factor of 10, or maybe by a factor of 1 or 2, and double. So that's why we can reduce the friction from 0.15 to 0.05 at some certain point, even when it reached to 270 degrees C. So, but when we apply this Docera MS5, which is having the same oil thickness, oil viscosity, but then with different additive, the trend for this friction is almost similar, but then slightly different. But the friction coefficient, the additive is activated around 200 degrees C, which is slightly lower compared to this. So then, but then it turns back, it goes up back again to its frictions when it reach about 240, 50 and above in temperature. So, but then for paraffin oil with no special additive, this is what happened. So meaning that the oil, the additive do not play around in this case, except that this one. So, which is more important? I think that's help to answer the second question. So then the third question is, which is more important for wear analysis, wear rate or or volume loss? To my knowledge, we for our investigation, the one I shown you earlier, we only for it depends on the mating materials. It depends on the lubricants and it depends on the and many factors that the process parameter. So if you ask me which one is very important, I would say that both are important, but to me wear rate is much more preferable in this case, because it's the constant where we determine the wear volume. We can give is the wear rate is a function of the influential factor that leading to this wear. Maybe some other tribologists also have some other opinions, but then for me, for my side, wear rate. So and then I hope that answer your questions. So is there any questions? Yeah, forgot to turn on the video.
Thank you, sir, for such a comprehensive and enlightening talk. I'm sure that all of us have learned immensely from it and entered a wider horizon of thought process as students and professionals. I'm sure those who like to apply their hardworking skills in manufacturing, which comes along with friction and lubrication, have learned a lot from this session. Having knowledge about these subjects is always very helpful while dealing with manufacturing process. And thank you again, sir, for clarifying all our doubts and questions. I'm sure that everyone now has a better understanding about the topic of friction and lubrication in manufacturing. After such an enthusiastic session, we will move on to a short break and return back onto our next and final session for the workshop by Dr. Jitendra Kumar Katiyar on the topic of application of hybrid nano-cutting fluid in machining of hard and soft alloys at 2 p.m. I hope the participants have not missed the link in the feedback form and have duly filled it up. All the participants, please be back on time as to not miss such an opportunity as the session will start at 2 p.m. As scheduled.
Thank you, Prof. Thank you so much for a wonderful talk on the tribology of manufacturing.
Yeah, thank you so much for the invitation to Prof. Rao and the organizer. Yeah.
Thank you.
So thank you, Professor Mohammed and Dr. TVLN Rao for gracing this function, for sharing your knowledge with us.
Thank you, sir.
Looking forward to have much more associations with you in the future programs.
Thank you, sir.
Yeah.
Thank you so much.
Yeah. Thank you. So now I may leave this chat, this room, right?
Yeah, sure, sure. Thank you, sir.
So thank you so much for this invitation. So I hope you could reach out to us for collaborations to my tribals members and also my tribologists at my university. Yeah.
Thank you, Professor.
Okay. Maybe later the organizer can share with me the video or the recording of these sessions.
Yeah, by end of the day, we will share the recorded video, sir.
Okay, thank you so much for this.
Welcome.
And okay. Okay, bye.
Yeah, welcome, sir.